So let's look at Newton's cooling law. So in Newton's cooling law, I would have already made a summary. So I'll quickly go through it. Then you can understand what are the things that you have to add to your summary. So in Newton's cooling law, what we do is we have an initial setup where we have filled liquid. The liquid is filled, and here we know that this setup is going to lose energy. This setup is going to lose energy, and that loss of energy for a given time, average rate of heat flow, that is given by Q over T, that is proportional to excess temperature. Okay, that is proportional to the excess temperature. This is the Newton's cooling law. Now we have the law, and now we need an equation. To bring that equation, we need to put the remaining constants. So we know that is Ka greater than excess. Then when we have a system where the K is same, area is same, and excess temperature is same, then it says the rate of heat flow is same. So that doesn't matter if we use water or another liquid. If these are maintained same for both water and liquid, the rate of heat flow should be equal. So we know that Q over T for water is equal to Q over T for that liquid. Then how can we write Q over T? That is MW SW delta theta plus C delta theta divided by time taken to drop to this temperature, have that temperature drop. That is equal mass of liquid, S of liquid plus C delta theta divided by TL. Okay, so this is the equation that we get. So now in this experiment, what we would do is we need to get this delta theta over TW. For that, we will plot the temperature versus time. Temperature versus time for a liquid and the water in a graph. So when we plot it, temperature versus time, when we plot the temperature versus time, for both the liquids, we will get a graph like this. So if water has higher specific heat capacity than liquid, it will come on top. The other one will be second liquid. Okay. So from this graph, we can find what's the time taken to drop from temperature theta 1 to temperature theta 2. So this is water. Then so the time taken to drop from theta 1 to theta 2, we can mention it as TW1 T. So this is for liquid, and this one is for water. So just like that, we can measure it from the graph, right? So once we know those, we can find MW. We can find ML, finding the mass. It's similar, right? First, we will take the weight of the calorimeter and stir only, then add the water and get that weight, get the difference. That will give us this weight, similarly this mass. So these two are known. Then SW is known, C is known, TW and TL that can be got from the graph. So everything is known except for this. Then what we can do is from this experiment, we can calculate the specific heat capacity of that unknown liquid. Now, in this experiment, so this is the overall experiment that you need to know. When we are conducting the experiment, we have to take into consideration a few things. When you're setting up, you need to take a few things into consideration. So let's see what are they. First of all, in Newton's cooling law, how is the energy loss? Energy loss are we have three methods of energy loss. Okay, what are the three methods? We have conduction, convection, and radiation. Okay. Now, how does Newton's cooling law lose energy? How should it lose energy? By convection, right? It should lose energy by convection. Then we have to minimize conduction and radiation. Now, how to minimize energy loss by conduction? How can we minimize that? One, we can isolate the system. We can hang this. We can hang this. If we hang this system, then it is not in contact with any other. So we can minimize the energy loss by conduction in this method. Otherwise, we can place it on a small bits. Okay. So by those two methods, we can produce the heat loss by conduction. Then we are done with conduction. What's the other method? Other method is radiation, right? Heat loss by radiation. How to minimize heat loss by radiation? We are using a polished calorimeter. So by using a polished calorimeter, we can minimize heat loss by radiation. Then what about using a lid? Do we need to use a lid? Do we need to use a lid over here? Why do we need to use a lid? What's the purpose? Conduction energy lose hang panni korchachi. Radiation also we reduced by using a polished calorimeter. Then why do we need a lid? Water can evaporate, right? Water or the liquid can evaporate. If it evaporates, then the mass we measure and the heat it has, all of them is going to create error because they are escaping from the system. So to minimize that, we can put a lid. Okay. So that's fine. What is the measurement we have to take? We need the temperature of the liquid. So we need the thermometer. Can we take the thermometer reading continuously? I mean, without doing anything to the system? No. What we have to do? We have to continuously stir this. So we need a stirrer as well. So we have to continuously stir and take the reading. So what are the readings we have to take in this system? Don't mention we have to take the temperature of the liquid. Don't say take the temperature of the liquid. Say take the temperature of the liquid at constant time interval. Okay. So the reading we take is temperature of liquid at constant time interval. Okay, we have to take it at constant time interval. So now let's go through the past papers and see if we get any new ideas when we go through those questions.
What's that?
So, now let's go through the past papers and see what we can find. And we need this. In 1991, now 1991 question, it is not method of mixtures. Sorry, it is method of mixtures question, not Newton's cooling law. But look at the first question. Sorry, second question. State the process by which the heat is lost in calorimeter. In a calorimeter, what are the methods heat can be lost? So there they have mentioned 4 methods: conduction, convection, radiation, and evaporation. Okay. So they have mentioned evaporation, and then come to (1998). In 1998, once again, that's a method of mixtures question. They are in one of the question they are asking, when we put the heated metal ball into the liquid, in addition to conduction, convection, and radiation, there's another heat loss. What is that? There, in the answers, they have mentioned vaporization of water, within brackets, not evaporation. Okay, evaporation illanu mention pannirukku. Now, what is the difference between evaporation and vaporization? What is evaporation? What is vaporization? When we say vaporization, vapor can form anywhere in the liquid. Okay, vapor can form anywhere in the liquid. When we say evaporation, where does it form? It's going to evaporate only from the surface. Okay, it is going to evaporate only from the surface. So vaporization, it can form anywhere. So boiling of water is vaporization. Evaporation, it's only on the surface. So here, is it vaporization or evaporation? Why are we using the lid? To minimize vaporization or evaporation? To minimize evaporation, not vaporization. In a vaporization, if vaporization has to occur, water has to boil. So the temperature should go above 100. But here, it not above 100, it should come to 100. So here, that doesn't happen, right? So here, it's evaporation, not vaporization. Okay. So that's a nice point to note down. Okay, let's look at 1997. Now this is different schooling. So identify the vessel A, is the calorimeter. What are the additional what are the additional essential measuring instruments required for this experiment? Now, in this experiment, from here we know that we need the thermometer and this stirrer, that is fine. In addition to this, what are the other things we need? So when we are taking the reading, we need to take temperature of liquid at constant time interval. So how to take constant time interval? How to measure it? You will need a stopwatch, right? So here for this, to measure this part, you will need a stopwatch. Okay, you will need a stopwatch. And then here we want to measure the mass of the water and the liquid. For that, we will need a triple beam balance or an electronic balance. So for these measurements, we will need the triple beam balance, right? Next, in this experiment, separate cooling curves are obtained for water and liquid. What amount of liquid has to be used with respect to that of water? So water and liquid, we have to use the equal volume. So what is the reason for that? To have the same surface area, to maintain the same surface area. Those are very common questions. Next, we need to draw the cooling curves. So that also can be done. Two quantities have to be extracted from the curve in order to determine the specific heat capacity of the liquid. Show the necessary construction on the diagram given in E in order to obtain these quantities. Okay, so from this graph, what do we need to get? We need to find this TL and TW, right? we need to find this. Otherwise, from this, we want to find delta theta over PW. Okay. Which one is better? Finding delta theta over delta T or d theta over dt. Which one is better? What is the difference between them? Delta theta over delta T and d theta over dt. What is the difference between them? Both of them look similar, but the difference is, now say we have a curve. In that, you take any 2 points and get this difference, delta theta, over this difference, delta t, by constructing a right angle triangle. So if we do this, this is delta theta over delta t. You get the gradient. Here, you are getting the average cooling rate. You are getting the average. What is d theta over dt? We get the same thing at a single point. Okay, we get at a single point. How can we get it? We need to draw the tangent to this point. Okay, we need to draw the tangent to this curve. How can we do that? What you can do, you can take a mirror and place it just like that. So you can see this image here. Okay. When the image is smooth and continuous, then the line we draw is 90 degrees. So when I see it like this, the image is broken. It goes just like that. Okay. When I place it like this, now this is the image was smooth. What I drew was normal to that line. Now what I have to do is draw normal to that. If I draw the normal to this, then I'll get the tangent to that curve. So if I get the tangent to that curve, I can get the gradient exactly at this point. Now I can find this over this. That will give me d theta over dt. Okay. So we can do the construction in 2 ways. One is we can do the construction like this to find delta theta over delta t, or we can do the construction as I mentioned. By that we can find d theta over dt. Okay, both of them are correct. Which one is better? Second one is better because Newton's cooling is not for 2 temperatures. It is for a single temperature. Okay, it is for a single temperature. So this method is better than this. So that's a good point to know. And look at the question H. Can you perform this experiment by filling the space between A and the outer with water? Now, in that diagram, they have something like this, right? In that diagram, they have the calorimeter. They have the calorimeter filled with water, placed inside another vessel and on a wedge. They ask, can we fill this outer vessel and this area with water and do the experiment? Can we do that? Can't. Why? So the surrounding temperature will change. But in Newton's cooling, we need the excess temperature. What is excess temperature? Theta minus theta r. This is theta minus theta r. Room temperature should not change. It should remain the same. Otherwise, the surrounding temperature. Here, the heat that is lost by this is gained by water. So this temperature over here will increase, right? This temperature increases. Therefore, it cannot conduct the experiment. So this is not possible. Okay. Okay, then we have 2006. In 2006, so the first question is a very common one. Why do we need to fill equal volume? We already discussed. Up to what level have to fill? L2, L3 or L1? L1. Okay. We have to fill up to L1. Maximum fill பண்ணுங்க. Water overflow. In this experiment, which temperature do we need? That's a very important point. Do we need the surface temperature or liquid temperature? We need the surface temperature. Okay. We need the surface temperature. What we measure? We measure the liquid temperature. So to make sure that the surface temperature and liquid temperature is same, we have to mix it well. Okay. Then mix the same reason. We are measuring the surface temperature. What we need is surface temperature, but what we measure is liquid temperature. So we need to make sure both of them are same. Then for that we continuously stir it. Yes, reason. Okay. Not to have a uniform temperature in the liquid. Uniform temperature equal to the vidavum, what we have to have? Wall and liquid should be the same temperature. Then the remaining question is same. Come to the last question. Why is not suitable to use a glass container in place of the calorimeter in this experiment? Discuss question. Now, if we are using a glass container, now say we are using a glass container. Okay, this is a glass container. So we know that glass is an insulator, right? Glass insulator. So what we measure, what we are going to measure? The thermometer is going to measure liquid temperature. So that is, let's say, theta1. Right? For our experiment, what temperature do we need? We need this temperature. That is theta2. Theta1 and theta2, are they same? No, because it is a very poor conductor. Because glass is a poor conductor, what we measure is going to be higher than what's the external temperature. Okay, theta1 will be greater than theta2. There will be a temperature gradient. So it will create errors. Then you can say why it is not suitable, right? The outer surface of the container and the liquid's temperature will be different. There will be a huge difference. There will be a temperature gradient. You can say these reasons. Okay. Next, we have in 2017, right? Now, 2017 is slightly different. Okay, look at 2017. Now, 2017 is slightly different from whatever we discussed earlier. What are the readings that you would take in this experiment to verify Newton's law of cooling? First of all, let's see what is Newton's law of cooling. Now, this one is the equation. Okay, this is the equation, but this is not the law. What is the law? Newton's cooling law. This one. This is the Newton's cooling law. This is the equation that we get from it. So in our case, we don't need this. Okay, just forget about that. Now, if we can prove Q over T is proportional to excess temperature, then we can prove the Newton's cooling law. We can verify it. So now Q over T proportional to excess temperature. This is the law. If this is proportion, then if I plot a graph between them, what type of graph should I get? If it is directly proportional, what type of graph we will get? Y is equal to mx graph. So if we can get a y is equal to mx graph, then we can verify this. Now, let's see what are the necessary measurements that we have to take. Consider water. We have water and it's fixed. And we are going to let it cool. Okay. So here, in place of Q over T, what I can put for Q? For Q, I can put MW SW plus C d theta over dt. Okay, d theta over dt. Proportion, what is excess temperature? Theta minus theta r. Okay, theta minus theta r. So here in this setup, what are the constants? MW SW plus C. How is it? it's constant. So even if I remove this part, still I must get y is equal to mx graph. இந்த part இருந்தாலும் இல்லாட்டியும் I should get y is equal to mx graph. So if I can prove d theta over dt is proportion to theta minus theta r, if I can prove this, then also I can prove or verify the Newton's cooling law. Is that idea clear? So if I want to plot d theta versus theta minus theta r, what are the measurements I have to take? So here in place of d theta over dt, we can take delta theta over delta t as well. Okay, in a average value. So what is delta theta over delta t? That's the temperature difference at a constant time interval. Okay, at a constant time interval, you need to measure the temperature. So if you are measuring temperature at a constant time interval, you have taken this measurement. Is that clear? And you also have taken this measurement. In a temperature 30 seconds per measure pandranda, you are taking theta, right? You are taking the temperature of the water. So this is measured. Okay. So what is the first measurement we have to take? We have to take temperature of water at constant time interval. Okay. What is the next measurement we have to take? Theta r. We have to take the room temperature. So the second measurement is room temperature. Okay. So that will be the answer for the first one. What are the measurements we have to take? Temperature of water at constant time interval, and next room temperature. What is the experimental procedure to perform? That is stirring, right? Draw a rough sketch of the two graphs that you would plot to verify Newton's cooling law. Newton's law of cooling. Label the axis properly with appropriate names. Okay, we have to plot two graphs to prove the Newton's law of cooling. So we can plot this graph. We can verify that d theta over dt, cooling rate depends on the temperature. So if we plot d theta versus theta minus theta r, what type of graph we will get? d theta dt versus theta minus theta r. If we plot this graph, what is the graph we will get? Mx graph. Y is equal to mx graph. Y is equal to mx. Okay. But so we are going to get the y is equal to mx graph. Next, what is the other graph we can prove? The same graph in another way. So we can show theta versus time. Theta versus time. So initially, it is at a higher temperature. Now, in a theta versus time graph, from this graph, what do we say? d theta over dt is proportional to theta minus theta r. So with time, what happens to theta? It will decrease. If this decrease, what will happen to d theta over dt? That will decrease. In theta versus t graph, what is d theta over dt? Gradient. So what should happen to the gradient? Gradient should reduce. So initially, it is starting with a higher gradient and then reducing. Okay. So here, look at the slope. It's a huge slope. As it moves forward, it is becoming flat, horizontal. So it eventually will reach to room temperature. Okay. So this is the two graphs that we can plot to verify the Newton's cooling law. Is that idea clear? How we got this graph and this graph? In order to determine the specific heat capacity of given liquid, The same procedure used in A above is repeated for the liquid after obtaining relevant readings for water. Why we are using the same calorimeter? To maintain the nature of the surface same. Why are we using the same volume of liquid? Same surface area. The remaining question is similar. Similar again. So now let's go through that question I gave. So in the question, let's go through the questions quickly. A calorimeter with shiny outer surface is hanged by using an insulated string and the experiment is carried out. Give the reason for the following. Using a calorimeter having polished outer surface. Why is that? To minimize radiation. Hanging the calorimeter using an insulated string to minimize conduction. Okay. அதில் வந்து 7 மணி வரைக்கும் mention to minimize. And you cannot 100% prevent it. You only can minimize it. So use the word minimize. That's the better option. A student considered that it is better to use an electric fan to cool the calorimeter instead of cooling it by placing it near an open window. Give the reason for it. Now, one more thing we forgot to mention here is that Newton's cooling law is applicable in 2 situations. What are they? One is natural convection, the other one is forced convection. In natural convection, what is the condition? Excess temperature should not be greater than 30. Okay, for natural convection, excess temperature should not be greater than 30. For forced convection, any excess temperature. For forced convection, any excess temperature. So remember that point. Then placing it close to an open window, placing it next to a fan is better. Why is that? We can get a uniform airflow than close to a window. Okay. Experimental procedure to make sure calorimeter wall and liquid has same temperature. Stir well continuously. What are the readings that the student needs to take to draw the cooling curves? Reading economy. What are the temperatures we have to take? Sorry, what are the readings we have to take to draw the cooling curve? We need to take the temperature of water at equal time interval, temperature of liquid at equal time interval. Do we need to take the room temperature? Room temperature தேவையா? Room temperature தேவையில்லை. உங்களுக்கு கூலிங் கர்வ் ட்ரா பண்றதுக்கு ரூம் டெம்பரேச்சர் தேவையா? உங்களுக்கு எக்ஸ்பெரிமெண்ட் கண்டக்ட் பண்றதுக்கு ரூம் டெம்பரேச்சர் தேவை. கூலிங் கர்வ் ட்ரா பண்றதுக்கு you don't need that. What you need the temperature of water at constant time interval, temperature of liquid at constant time interval. அவ்வளவுதான் தேவை. Okay, so those are the 2 readings we need. Is it clear why we do not need the room temperature? And like experiment like use pandradhukku, once we have done the experiment, finally we will need it here. But to draw the curve, we not need it. Okay. So the cooling curve is given after drawing it. Draw the cooling curve which is obtained for the liquid by comparing with the above curve. Heat capacity of liquid is less. Now, once again, here this is the cooling curve of water, right? This is the cooling curve of water. How can we draw the cooling curve of liquid? It will be above this or below this? It will be below this. And what is the starting temperature? We should start from the same temperature and reduce. Okay. So it should start from the same temperature and come down. Then you can mark time taken, right? as here. Okay, so they have marked theta 1 and theta 2. And there in that curve, there is also theta r. The curve theta r means can that line go below theta r? Can it go below theta r? Can't. In a theta r, it is reaching theta r. Okay, it is reaching theta r. Therefore, it should not go below theta r as well. I think கவனமா பார்த்து ட்ரா பண்ணுங்க. தெரிஞ்சாலும் வேற இல்லை. அப்படி கீழே எடுத்துட்டா no marks. What you can say about the heat loss? What you can say about the rate of heat loss of water and liquid during the time period in which the temperature dropped from theta 1 to theta 2? What can you tell about that? Heat loss. Same or different? It's same, right? What is the difference between rate of heat loss and rate of cooling? Is it same or different? Rate of cooling and rate of heat loss? It is different. Rate of heat loss means dq over dt. Rate of cooling means d theta over dt. So is the rate of cooling same for liquid and water? Which one's rate of cooling is high, liquid or water? So d theta over dt is the rate of cooling. So this one's curve is more steep than this one's curve. So rate of cooling of rate of cooling of liquid is more than the rate of cooling of water. Okay. So don't get confused with rate of cooling and rate of heat loss. This term is usually confusing. So rate of cooling is d theta over dt. Rate of heat loss is dq over dt. Okay, both of them are not same. They are different. Now, once you try this whole set of past papers, confident on Newton's cooling law, you can approach. And you are going to see the same question again and again, but there's one question that's slightly different. So you must be able to approach that because you have some sort of background knowledge about this section now. Alice. Next, let us look at RH using dew point. RH using dew point. So in this experiment, how we conduct the experiment? What's the equation? We know that RH has multiple equations, right? RH is M over capital M into 100%. So absolute humidity over saturated humidity into 100%, the ratio between them. So we can get the same values using SVP as well. Okay, we can get it using pressure. So we can get it using the pressure at a given temperature over the SVP at that temperature, or we can get the same thing using SVP. We can get simple M using SVP, capital M using SVP. So RH is equal, in place of simple M, we have SVP at dew point over SVP at room temperature into 100%, right? This is the equation we can use. So we can find, we have this chart. We have SVP chart. We have SVP chart, a general chart in the laboratory. So this part, you don't need to worry because there's a chart. But to find the SVP, we need to know the temperature. We need to know what is the dew point temperature and what is the room temperature. So once you know the dew point temperature and room temperature, you can get it from the graph. From the graph, we can get these values. So let's say the graph SVP versus theta. It's a graph something like this. So if you know the dew point temperature, you can get it SVP value. You know the room temperature, you can get the SVP value. Then you know these two values, we can get the ratio. So in this experiment, what we have to determine? We have to determine the dew point. Room temperature, we can find it easily. So if we can find the dew point, finding the SVP is not that big deal because we have the chart, we will get it from it straight away. Okay. So how to find the dew point? That's the main thing. Not that hard. What we have to do? We will fill a calorimeter with water. For how much level should we fill? Can I fill 1 centimeter below? Can't. Why? Ice cut. Okay. So we shouldn't fill this for below 1 centimeter. We have to fill half or below 1/3. Sorry, 2/3. Okay. So somewhere over here, you can imagine, you can understand, right? Ice cut boda kotta badadi. Adika nallave thanni kora omiki badadi. Nallave thanni kora indane enna problem. Inge dew point inge madala form. If you have very little water, you cannot see the dew forming. If you have too much of water, you put the ice cube, it overflows. Those are problems. So fill it somewhere in the center. Okay. Now, so what are the instruments we need? What are the instruments we need here? We need a stirrer. Before that, we need a thermometer. And we need a stirrer. What type of stirrer? we need a Squarnett stirrer. Why we need one? Like if you keep the ice underwater, it will quickly absorb energy. Then absorbing energy from the surrounding, it will absorb the energy from water. Okay. You can have a normal stirrer or a Squarnett stirrer. No problem with that. The stirrer is also just to mix the ice. So you can say stirrer or a Squarnett stirrer, no problem. So what we do, we drop ice cubes and stir it. Then what will happen? Dew will form. When dew forms, we will measure the temperature θ1. After that, what we will do? We will stop stirring and adding ice and let the dew disappear. So when the dew is disappearing, once again, we will measure temperature θ2. So temperature when dew appears is θ1. When dew disappears, when dew appear θ1, when disappear it is θ2. So what is the dew point? The average between them. Now, ஒரே temperature தான் சரிக்கு trend நடக்கணும், but there might be slight difference. So the dew point is average of them, θ1 plus θ2 divided by 2. Okay, that will be the dew point temperature. Now, what type of calorimeter should we use here? What type of calorimeter should we use here? A polished calorimeter. What is the reason? To see the dew forming, right? We can see it becomes blurred. When dew forms, it becomes blurred. Here, are we worried about heat loss? Conduction, convection, radiation, are we worried about this? Minimize pananuma. Not necessary. Okay? This doesn't matter. And I'm the heat loss. We just want to find out what's the dew point temperature. So the main purpose of using polished calorimeter is to clearly observe dew formation. Okay. So in 1993, we have a question. Let's see if we can find anything useful from these questions. So the first question, what is the other instrument needed? So thermometer. What is the purpose of well-polished outer surface? To observe the dew formation and disappearance very clearly. What is the measurement you would take in this experiment? Temperature when dew appear and disappear. Which one is better? Using small ice cubes or large ice cubes? Small ones. Why? Control on the you put a large ice cube and now dew starts to form. Now you cannot remove it. Then dew will form and make droplets of water. When it becomes droplet, then it will start to come down and also it will not disappear easily. So it's problematic. You should form. At that time, we should ideally stop the experiment and let it disappear. So if we use small ice cubes only, we will have control. So if you add ice cube after dew is formed, what will be the problem? Large water droplets will be formed on the surface. When some water vapor is removed from air, the dew will not disappear at the same dew point. I mentioned earlier. Now you want to find the RH. They have given the graph I mentioned earlier. So once you know the dew point temperature at 24 degrees Celsius, from that graph you can find the SPP. and at 30 degrees Celsius, you can find the SVP, and you can get the ratio. Okay, so then we can get the RH. In 2003, you have a question. So in 2003, all the questions are similar, so no problem. Look at the last question, question F. When you blow your breath on a polished metal surface, you can observe that the surface brightness is being reduced. Explain the reason for this. Now, when you blow your breath on a polished metal surface, you can observe that the surface brightness is being reduced. So we know that when you blow the breath, now it's going to produce dew on the surface. Now they ask, why is that? What's our body temperature? Doctors? 37 degrees Celsius, right? So inside our body, the temperature is high. There'll be more water vapor. Okay, when we exhale, you're going to have water vapor. That is, we know that when temperature increase, the amount of water vapor that can be in the air also increase. So there'll be more water vapor concentration, and the outer surface surrounding is in what temperature? Room temperature. It is below 37. So when we blow our breath, that temperature is low, and from inside the body it's high. Then we are going to have more water vapor concentration. Then the dew point is going to be high, right? And when do we get the dew point? Dew point, does it depend on the temperature? Does dew point depend on the temperature? Does the dew point depend on the temperature? It does not depend on the temperature. Okay, dew point does not depend on the temperature. Can we have dew point above room temperature? எனக்கு room temperature மேல dew point கேளுமா? room temperature கீழே room temperatureல எல்லா டெம்பரேச்சர்லயும் கேளும். room temperature கேளும், room temperature மேலே கேளும், room temperature கீழே கேளும். எப்ப dew point வரும்? When do we get dew point? We get dew point if RH is 100%, then that temperature is dew point. Okay. If RH is 100%, that temperature is the dew point. So it can be above room temperature, it can be below room temperature, or it can be at the room temperature. So it does not depend on the temperature. Okay. So in this case, when we exhale, the dew point is higher than the room temperature. Therefore, it will form dew on that glass surface or the metal surface. Okay. This one we have discussed in theory. Just recall it. Any good example, room temperature male dew point varumradhukku. Now you boil water and keep some piece of metal or whatever in its vapor. Will dew form? Yes. What is the temperature? Almost 100, right? So it is way more above room temperature. Then you can have it. In our RH 100% DU. We will have more water vapor. And we can have at the room temperature. An example for RH at room temperature. Now you are in a closed room, no fan, nothing. After some time, the room is very, very hot. You sweat, but the sweat doesn't evaporate. So room temperature and dew point is now same. That's why it's not evaporating. Okay. So you can have at the same temperature above room temperature, below room temperature. Then we have the RH question in 2021, right? So what is the appropriate level to fill the water? It's D. And they ask what thermometer shall we use here? Here we need to use a thermometer. They have given three options. The first option is minus 10 to 50, minus 10 to 100, minus 10 to 200. Which one is better? Minus 10 to 50. Yes. So which one is better? Minus 10 to 50. What's the reason? Minus 10 to 100 use பண்றது விடவும் minus 10 to 50 use பண்றது better. Why is that? Now, just think, if the thermometer is measuring for a higher range, then those calibrations on the thermometer, the calibrations will be very, very close, right? If it has to measure a huge range, the calibrations will be very, very close to each other. But if it has to measure a smaller range, then there will be better gap between them. So this thermometer is more sensitive than the one that is having a higher range. So which one is better? Obviously, the one that has more sensitivity is better. So we can use the thermometer with minus 10 to 50 degrees Celsius. So when you are using this thermometer, you have to be careful about the mixture's temperature. Mixture temperature engikum அப்படின ஒரு ஐடியா ஒண்டிக்கணும். Now let's say mixture's temperature. Now this is method of mixture's experiment. And the temperature is going to come close to 50. In that situation, if this question is in method of mixtures, can I use this thermometer? Can't. In that situation, what is the thermometer I have to use? Minus 10 to 100. Okay. So just because it is sensitive, adanala idu use pannom, don't think like that. You have to think mixture temperature enga varum and it is sensitive kuda. Which one is easier to read? You have to think all of this and select that proper thermometer. Okay. What are the other important items necessary to perform this experiment? It is not given. Stirrer or stirrer with a mesh. So the other one is also okay. If the experiment conduct பண்ணி that you know. That's also okay. What is the now here in question number F? They ask, what if we use 0 degrees Celsius water instead of 0 degrees Celsius ice? So instead of water, if I use ice, here I only want to decrease the temperature. Temperature must decrease panna. So we can mix water or mix ice. But which one is better? Ice is better. That's why you'll be using ice. Now, what's the disadvantage if we use water? Now, when we add ice, first ice has to go from 0 degrees Celsius ice to 0 degrees Celsius water. In that time itself, it will absorb a lot of heat. for that phase change. அப்ப அந்த டைமுக்கே நிறைய heat absorb பண்ணிரும். Then the amount of ice we have to add is less. But if we are adding water, it starts from 0 degrees Celsius water. So we will have to add more water than adding ice. So it's obviously disadvantage, right? When you add water, it might spill over even before reaching the point. Okay. Give two errors that can occur if the transparent glass is not used. What are the errors that can happen if you are not using a glass sheet? So they have asked for two errors. Does anyone have? Okay, we can tell one reason. RH will change in that region because when we exhale, now it's going to become a mixture. Surrounding and the one we exhale, both of them are going to mix and give the result. So that's one problem. It will change the RH. And the other one would be temperature close to the calorimeter will change. Now, what you breathe out is almost 37 degrees Celsius, and room temperature is different. So, what we are going to get is a different temperature. So, that's going to interfere with once again the RH. RH का मार दूँ मेरे बाद मैंने और ये चीज़ ना then has bus right. Yeah, we can have two errors. One is the RH actually can change. Second one is even before this dew forms due to lowering the temperature, when we exhale, that itself can form the dew, right? Exhale the direct away dew form pannidum, because the breath we exhale is having dew point above room temperature. The question that we discussed earlier, previous year, on the metal plate, like A form adhu reason enna dew point above room temperature. So when we exhale, it will directly form the dew straight away, and that's one error. And also it will change the surroundings RH. Okay, so we have two errors. So we can say due to exhale, breathe, striking the parameter. That's one error. And also it can actually change the RH around that area. Actually change RH of the surrounding. Okay, it can actually change the RH of the surrounding as well. So those two problems can arise. So to avoid that, we can use a glass plate. Now they have given a few dimensions, LMN. One is 5 by 5, 20 by 20, 80 by 80. So which one is better? 5 by 5, 20 by 20, or 80 by 80? 20 by 20 is better, right? 20 by 20, sorry. 20 by 20, keep it aside. 80 by 80, what is 80 centimeters? It's around a meter. So somewhere around this. Now you put that screen around that. How do you go to? Can you reach the calorimeter? Can't. Okay. So no, it's not possible. So 80 by 80, it's not possible. Then 20 by 20, it is someone around this size, which is sufficient. Okay. So you can think that way. Although at least your knowledge on 80 by 80 na size ni. 80 centimeters. Not millimeters. So what is the reason for not selecting, right? Select so why not select 5 by 5? That is too small. It will not make a difference. And the other one, too large, it disturbs us even doing the experiment. Okay. In this experiment, average value of dew point and laboratory temperature is 26 degrees Celsius and 30 degrees Celsius. Determine the RH of the laboratory using the graph given in the figure 2. In this graph, have we seen this graph earlier? No, but at that moment, you need to understand what you can get from this graph. In that graph, on one side, you have dew point. On the other side, you have laboratory temperature. And there are some lines. So, on the dew point side, check the dew point temperature. Okay. And along this line, when you move along this line, it is going to cross these graphs. Check the graph which crosses the room temperature. So room temperature is at 30. Upon the 30 and 26 process graph. And the graph for a cut panel, that should be the RHL. So it's crossing which graph? At 80%, right? 80% is crossing 30 and 26. It's like bit of a nice question. So from that moment, and got a viewpoint and leaving at a laboratory temperature and the when intersect our point, how we understand money, you must be able to get the answer. So RH is 80%. So the next experiment is getting the pressure, proving pressure versus temperature. So in this experiment, when we want to prove the pressure versus temperature, in verifying, what we have to do is, if pressure is proportional to temperature, we must get pressure readings, we must get temperature readings, and plot it in a graph. If we plot P versus T, we must get a y is equal to mx graph. Okay, we must get a y is equal to mx graph from these data points. So if we are getting y is equal to mx graph, then we can say that P is proportional to T. That is how we verify these laws. So let's straight away go into this question. And what's the experimental setup here? We have a round bottom flask. We have a round bottom flask connected using a capillary tube to a pressure gauge. Okay, connected to a capillary tube using a pressure gauge. Now here, how do we conduct the experiment? We want to measure pressure and temperature. We want to measure pressure and temperature. So we can use a Bunsen burner to heat this setup. We can use a Bunsen burner to heat this setup. Okay. We want to measure, what are the measurements we have to take here? We have to measure the temperature and the pressure. So let's see how to measure the temperature. We need to place a thermometer and we need a stirrer. So we have to continuously stir it. Before taking the temperature reading. And by the way, in this experiment, we want to measure the temperature. Whose temperature do we need to measure? Temperature of water or temperature of gas? Temperature of the gas. But what are we measuring? Temperature of water. We have to make sure that this temperature and this temperature is same. Okay. So what are the experimental procedure we can take to make sure this temperature and this temperature is same? One is continuously stirring. One is continuously stirring. What's the other procedure? We can make sure that this temperature and this temperature will become equal. Yeah, we can use a thin wall flask. But that is a fix, right? Change panel. One thing that we can do is we can slowly heat. Okay, we can slowly heat it without having a very high flame. We can heat it slowly. So we know that glass is a poor conductor of heat. Air itself is a poor conductor of heat. Air is poor conductor, glass is poor conductor. So we should make sure that the heat that is going here goes into this flask. So we need to heat it slowly, giving it enough time for that heat to spread inside. Okay, if we heat fast, what will happen? Water temperature high item, air temperature on the low item, what we are measuring is totally different. Okay, there'll be a huge difference or huge error between them. So we have to heat the liquid. Okay. And where else we can have problem in this experiment? This is the air. Now this flask will be inside water. So here, what type of tube should we use? Narrow tube. Okay, we should use a small capillary tube. Why is that? To minimize the air that is not in contact with water. To minimize the air that is not in contact with the water. Okay, because this air will be at a different temperature. So we want to minimize it. To minimize that, we are using a small capillary tube. So the pressure flow can be applied to a gas if and only if two of its quantities are kept constant. What are those quantities? What are the quantities we have to keep constant? Volume of the gas and amount of gas, otherwise the number of moles of gas. What is the reason a narrow tube X is used in the above setup? Why are we using a narrow tube X? To minimize the air that is not in contact with water. Okay? To minimize the air that is not in contact with water. To carry out the above experiment, two things are essentially needed. Draw those two things in the above diagram. What are the two things? We need the thermometer and the stirrer. Explain why the temperature of the water should be raised slowly in this experiment. Gas is a poor conductor of heat. So the temperature of water rises quickly, but air will rise slowly. So it needs time for it to come to the same temperature. Therefore, we have to increase the temperature slowly. How would you confirm that the air in the bulb has attained a steady temperature? How can we confirm that the air is at a steady temperature? This pressure gauge reading will be constant. It will not change. If it is changing, if it is increasing, that means it is still not at a steady temperature. State two important procedure that you would use to maintain the temperature of the water at a particular value. How can we maintain at a particular value? One is stirring. The other one, move the Bunsen burner in and out. Moving the Bunsen burner in and out. Okay. Because we know that when we heat it, temperature will keep increasing. Then when we stir it, it will spread for every place and it will start to drop. Then if you want to maintain at a certain level, we will need to put the Bunsen burner in. to once again bring it up. And in the mela podun sonna cool out, so you take it out. So you play with it to maintain at that level, in and out. So you want to maintain at same level, and the pressure constant. Draw the rough sketch for the variation of gas pressure with temperature theta. So when they say temperature theta, they are measuring it what? They are measuring in degrees Celsius. Okay, they are measuring in degrees Celsius. So this, if we plot it with absolute temperature, if we plot the same graph with degrees Celsius, we will get a variation like this, right? Okay. So be careful with this temperature. If they mention theta, it's degrees Celsius. If they mention capital T, it's Kelvin. Next, this pressure gauge. It will read what pressure? Pressure gauge. This will read gauge pressure. Okay. This pressure gauge will read gauge pressure. Gauge pressure means the pressure difference from the atmospheric pressure. So let's say the atmospheric pressure is 180 m. Atmospheric pressure is 180 m pressure. And this one is reading 180 m pressure. This one's reading is 180 m pressure. Then what is the pressure? Now the pressure is 280 m. Is it clear? This one is reading gauge pressure. So if it is reading 180 m, it is 180 m above the atmospheric pressure. If this one is reading 280 m, then what's the pressure? 3. Okay, so you will have to add the atmospheric pressure to get the actual pressure. And the actual pressure, you will have to add the atmospheric pressure. Then only you will get the actual pressure. So at 127 degrees Celsius, ideal gas reads a pressure of 1 into 10 to the power 5. So they say at 127 degrees Celsius, how many kelvins? 400. So at 400 Kelvin, pressure is proportional to temperature, right? So at 400 Kelvin, they say it is reading 1 into 10 to the power 5 Pascal. Atmospheric pressure of 1 into 10 to the power 5. Then what is the? It is 2 into 10 to the power 5 because it is reading 1. That's the gauge pressure. But actual pressure is 2. So 2 into 10 to the power 5 is proportional to 400 Kelvin. When the temperature is increased to 177. 177 means 450. So P is proportional to 450 Kelvin. What would be the reading of the pressure gauge? What will be the reading of the pressure gauge? So let's divide. P over 2 into 10 to the power 5 is equal 450 over 400. So we can divide it by 50, then 9/8. Then P is equal 9/4, that's 2.25 into 10 to the power 5 Pascal. Now, what is this pressure? This is the actual pressure. Then what will be the gauge pressure? We have to deduct that atmospheric pressure. Then the gauge pressure will be deduct that one, then 1.25. Okay, so 1.25 into 10 to the power 5 Pascals. The last question. Instrument examine pressure equal to atmospheric pressure atmospheric pressure Okay, look at the last part. The air in the flask will not have the same temperature as water. To clear this fault, suggest a step that can make the temperature of air and water be equal. What can we do? திரும்பவும் ஸ்டே பண்ணேன். ஏண்டா அங்க எக்ஸ்பெரிமெண்ட் ஸ்டார்ட் பண்ணவங்க என்ன சொன்னோம்? டு மெயின்டைன் தி டெம்பரேச்சர் ஸ்டே. அதையும் தாண்டியும் எரர் வரையிலும் இப்ப என்ன செய்யணும்? ஸ்டே பண்ணா டெம்பரேச்சர் சேம் ஆகும் நீங்க சொல்லிட்டீங்க. ஓகே, ஸ்டே பண்ணா டெம்பரேச்சர் ஆல்மோஸ்ட் சேம் ஆகும். அப்பயும் எரர் ஒன்று வரும். என்ன செய்யுது? யூ கேன் ஸ்டே பண்ணிடு. Does it make sense? No, right? So ஸ்டே பண்ணுன்னு சொல்லியாச்சு. அதே எரர் சொன்னா அதுக்கு என்ன செய்வீங்கன்னு கேட்டா அதுக்கு என்ன ஸ்டே பண்ணுன்னு சொன்னா doesn't make sense. So we need something else. What we can do is we are increasing the temperature, right? We are increasing the temperature. So when we are increasing the temperature, we can take reading. When we are decreasing temperature கூட்டினா டெம்பரேச்சர் குறையணும் தானே. So when we are decreasing the temperature, once again we can measure the pressure at that temperature. So when going up at theta 1, theta 2, theta 3, we will measure the pressure T1, T2, and T3. When coming down, when temperature is reducing, once again measure the pressure T4, T5, T6. Okay. Now what we can do? We get the average, right? We can get the average values. So by this method, we can somewhat minimize the error. Okay. So stirring is not the answer. அதெல்லாமே So now we Last question, they are asking how to make the temperature of air and water equal, right? I thought that time temperature different item, how we can minimize the error. But the question is different. It says how to make the temperature of air and water equal. Then save பண்ணி சரி வர அந்த நைட் நான் சேவ் பண்ண சொல்றேன் very slowly for this. How can we ஷூஸ் பண்ணாதன்னு கீழே அது வந்து வாட்டர்ல தான் எல்லாத்தையும் ஈக்குவலா ஹீட் சப்ளை பண்ணும். When you are using a now, if you think using a wire mesh will help, if you put a wire mesh here, what happens is the wire mesh will heat up and the heat will spread everywhere and heat the water uniformly. Okay, it will heat the water, not the air. One thing we can do is once 100% achieve something, you can get closer to achieving. So temperature of water and air equal பண்ண மெத்தட் ஒன்று இல்லை, ஃபுல்லாக ஈக்குவல் பண்ணுறதுக்கு மெத்தட் ஒன்று இல்லை. பட் we can get a better value by using a smaller bulb. Without using a larger bulb, we can use a smaller bulb. Because mixing, moving the Bunsen burner in and out, everything we have told earlier, the only thing that we didn't tell is using a smaller bulb. If you're using a larger bulb, then what's the problem? Air is already a poor conductor, so it will not spread the heat equally. But if it is a smaller one, then what it can do? It can easily spread the heat uniformly and come to a common temperature. So one solution would be using a smaller bulb. Okay. So what I told earlier would satisfy if the question was how to minimize the error. But if you want to have equal temperature, we will have to use a smaller bulb.